The talk will be starting with guided equality saturation, and the speaker is Thomas Koehler. Thomas started this work during his PhD at the University of Glasgow and is now a postdoc in the CAMUS team of Inria. He is interested in building tools for safe and interactive whole program optimization. This paper introduces guided equality saturation, a semi-automatic rewriting technique that enables equality saturation to scale by allowing human insight to guide the process at the key points. The authors demonstrate its effectiveness through case studies in theorem proving and program optimization, presenting a promising direction for future research that combines human intuition with the power of automation. Please take away, Thomas.
Thank you. Can you hear me?
Yes, we can hear you.
So thank you for the invitation and for selecting our work. This is joint work with my colleagues Andres and Siddharth, as well as our supervisors Tobias, Phil, and Michael. Sorry?
Can you hear us? I think the mic is little.
Yes.
I think the mic is a little blurry. Can you set up the mic more properly, or probably?
So is it too loud or not loud enough, or?
Can you talk again?
Is this better?
No, it's still blurry. Okay, can you take off the headset and use other mic?
Okay. Is it better?
I think it's still blurry. Can you talk? Are you using computer mic?
Yeah, now it's my computer mic. It's either the computer mic or the headset mic. Which one was better?
Can you log out and rejoin? Sorry.
Can you hear me?
Yeah, much better.
Okay. So I'll just keep going then. Imagine that you want to optimize.
Screen sharing.
There's no more screen share. Okay.
Yeah, perfect.
Imagine that you want to optimize a program so that it uses less memory. For that, you might define a rewrite rule, such as the one shown on the left, which takes a pattern, such as map A, map B, and replaces it with another pattern, here map AB, which uses less memory. The problem is that if you try to optimize the program shown on the right, you cannot apply this rewrite rule, because so we are in a local optimum. Does this mean that we cannot use less memory for this program? No. In fact, we can define two additional rewrite rules that, even though they have no effect on memory, they enable us to apply the first rewrite rule. So in this case, if we apply rewrite 2, then rewrite 3, we can then apply the first rewrite rule twice and find a global optimum that uses less memory. We cannot do this by using standard greedy rewriting techniques, because they would not apply rewrite rules that do not reduce memory immediately. This is why we use equality saturation, which mitigates the problem of deciding in which order to apply which rewrite rules when optimizing programs. The idea is to first initialize an equivalent graph, also called an E-graph. At this stage, the E-graph looks mostly like an abstract syntax tree, except that the solid boxes are called E-nodes, and they point to dashed boxes that are called E-classes or equivalent classes. Things become more interesting when we start applying rewrite rules. So here we apply the second rewrite rule that I showed earlier, and this simply results in recording the equivalence between the left-hand side and the right-hand side of the rewrite rule. By contrast to standard rewriting that would destructively replace the left-hand side with the right-hand side. We can apply more rewrite rules to this using equality saturation. And after applying, for example, rewrite rules 3, 1, and 1, our E-graph efficiently represents many equivalent terms thanks to these equivalence classes. Once we have grown an E-graph by applying multiple rewrite rules, we can finalize optimization by extracting a term from our E-graph that minimizes, in this example, memory usage. So here we are able to find the global optimum that I mentioned earlier, thanks to equality saturation. So equality saturation is a powerful technique, but it also has limitations. Here we are making the optimization problem a little bit more difficult by adding 2 additional rewrite rules, 4 and 5, and changing the objective from reducing memory usage to improving memory access patterns. So we're trying to apply a standard optimization, which is called loop tiling. To apply one-dimensional tiling with these rewrite rules, it is fairly easy using equality saturation. As you can see on the graph on the right, we only need one iteration of equality saturation and the memory footprint is low. Here by one iteration, I mean that on each iteration, we apply all possible rewrite rules in a breadth-first fashion. If we move on to two-dimensional tiling, things become a little bit more challenging. Now we have to not only to use the 5th rewrite rule, but also the 4th rewrite rule. We need 6 iterations of equality saturation, and we have a memory footprint of a couple of megabytes. And now if we look at 3-dimensional tiling, this is where things become tricky. We observe that the E-graph is growing extremely rapidly, and in the 8th iteration, we have already exhausted a budget of 8 gigabytes of memory. More generally, the problem is that when we are trying to reach a final goal using equality saturation, it is common to run out of resources because equality saturation is an expensive rewriting technique. To solve the problem, the key idea of our paper is to allow experts to guide the process by providing intermediate goals that we call guides. By providing multiple guides, the expert breaks down a single complex and infeasible equality saturation search into multiple simpler and feasible equality saturation searches. If we go back to the 3D tiling example, we can provide an intermediate goal or guide that encodes the insights that when we are trying to perform tiling, we can first try to split the loops in a certain way. So this is using the rewrite rule that was colored in blue color, and then try to reorder the loops, which corresponds to the rewrite rule in orange. Guides don't need to be complete terms. They can be more or less precise sketches. So here, for this example, we can just say that we are looking for a term that contains a certain nesting of map patterns. by providing these single guides, we are making our 3D tiling goal reachable with 8 gigabytes of memory. So without guidance on the left, we were unable to find our goal after 8 iterations, exhausting our memory budget. And on the right, we've now broken down this complex search into 2 simpler searches. The first one finds our intermediate goal or guide in 6 iterations. And then from there, we start a second search, which finds the final goal in 7 iterations. So beyond this example that I've showed to explain the basic principles, we have performed a more complex program optimization case study where the objective was to reproduce matrix multiplication optimizations from TVM. TVM is a popular domain-specific compiler for machine learning, and the optimizations that we looked at are about transforming loops, changing data layout, and adding parallelism. There was already prior work that showed that it is possible to perform these optimizations by manually composing rewrite rules on a language that is similar to the one I've been showing so far, so with these map patterns. What we wanted to do was, instead of requiring manual composition of rewrite rules, we wanted to automate this process using equality saturation. So we first tried to use unguided equality saturation to find our different optimization goals. So in this table, you can see 7 different optimization goals that are going from the simplest, which is the baseline at the top, to the more difficult goal, which is parallel at the bottom. And you can see whether unguided equality saturation found the goal, with which runtime, and using how much RAM of memory. So what we can see is that 5 of the goals are too hard to find with unguided equality saturation. And this is sometimes even after an hour of runtime. And overall, we gave up after when the search was taking more than 60 gigabytes of RAM. You can also observe on the right how the size of the eGraph data structure evolves through 2 of the searches. And you can see that the growth of the graph is very rapid and that we reach millions of nodes. Now, if we use up to 3 guides that are eliding about 90% of the complete program that we are looking for, we can now find all of these optimization goals using a couple of seconds and less than 1 gigabyte of RAM. And in particular, if we look at the blocking optimization, we can find this optimization goal about 600 times faster and using 100 times less memory, thanks to a single guide. On the right, you can see that the eGraph growth is not as extreme, because now we are looking at thousands of nodes instead of millions of nodes. So this was our program optimization case study, but we also wanted to show that our technique is more broadly applicable than this one case study. So we looked at theorem proving, and we implemented a tactic that is called GES for the lean theorem prover. In particular, Andres and Siddharth work on this case study. Using this tactic, and that integrates our guided equality saturation technique, we can prove theorems by writing a series of equalities. So here it is an example from group theory, where we want to prove that the inverse of G is equal to G. And we can prove this theorem using our tactic by providing a single key reasoning step shown in blue, which allows us to omit multiple rewrite steps and details, as you can see at the bottom. So, for example, we don't need to precise which rewrite rules are applied, and we elide three intermediate terms. Beyond theorems from group theory, we also looked at proving theorems on rings of characteristic 2. And on the left, the first thing that we observed is that guided equality saturation allows finding proofs orders of magnitude faster than without any guidance, and has a negligible overhead compared to a manual approach where all of the rewrite steps are detailed. On the right, we were also interested in looking at how picking different combinations of guides impacts the search. And what we noticed is that often it is important to find good guides rather than providing many ineffective guides. So here, only one good guide is enough, and we can four of the other guides were not so effective. To conclude, guided equality saturation offers an effective trade-off between manual and automated rewriting. For program optimization, guides resemble explanatory code snippets that you might write on a whiteboard. And for theorem proving, guides resemble key reasoning steps that you might find in textbooks. You can find more details in our paper, supplementary material, and our code is also open source. For the future, we have many ideas in which to improve this work. First, increasing the expressivity of sketches. If we want to enable users to specify which programs they are looking for with more flexibility. We are also interested in proving more challenging theorems from textbooks that may require more advanced term rewriting features. Generalizing this technique to imperative code optimization, which presents challenges for equality saturation in particular. And finally, we're interested in improving the user experience and exploring how to provide effective feedback for the user. Broadly speaking, I'm very interested in exploring more combinations of human intuition with automation. Thank you for your attention, and I'm looking forward to your questions.
Thanks for the great talk, Thomas. And we will open the questions. If any in-person attendees have questions, please raise your hand, and any virtual attendees, please raise your virtual hands or post the questions on the chat, then I'll read it for you.
Thanks for the talk, Thomas. I have a question about your first case study on program optimization. So I think equality saturation is not meant to not designed for automating scheduling for TVM. There is existing work on auto TVM answer that is specifically designed to search the program optimization space, right? I think my first question is have you compared against those techniques, and also do you see your work applied in those existing auto scheduling techniques?
Thanks for this question. So I haven't compared directly to answer because what our baseline here was an expert written schedule. I think it would be interesting to compare to these tools. But yeah, I guess here the focus was mainly, can we scale equality saturation and can we reproduce expert written schedules? And I think in the future, it could be interesting to explore how this compares to auto-scheduling techniques, and maybe how sketch guidance could be used, could be combined with these other search techniques.
Thanks. This was cool. Are you planning to add your GES tactic to Lean's MATLAB library of mathematics? It could possibly be quite useful there.
So I think Andres is online. Maybe he can answer this question directly.
Sure. I mean, short answer is something like that. Probably not MATLAB itself, but like as a standalone tactic that you could just yeah. So we're working on extending it, and Marcus, who's also here, is working on extending it and making it like more generally useful for sure. Yeah.
There's one online question. It says, from John Hui, can you intuit why certain combinations of rules lead to exponential growth of the E-graph? Are there any heuristics to automatically suggest that a sketch may be necessary?
Right. So there is work from Max Wilsey and Zachary Tatlock on identifying which sets of rewrite rules lead to an explosion of the E-graph growth or not. And I think that there are some heuristics that you can use. For example, if you look at a rewrite rule, you might be able to know whether it will create a lot of equivalence classes or whether it will only reduce the amount of equivalence classes, for example. So I think that I could imagine in the future a tool that lets you know whether your set of rewrite rules is likely to create to lead to a very quick blow up of the E-graph size. So I think that could be interesting to explore in terms of user experience.
Oh, there's one person raising a hand in the Zoom. You can turn
Oh,
on.
yes. Yeah, great talk. So I have one question, which is, so I can think of a variant of the sketch guided EQ set algorithm, which is instead of the user providing a sketch, in each, like once in a while, we extract the best program result using a sketch, and like we initialize the E-graph with that optimal program from before. So, and this is kind of like a beam search, right? Because you are kind of refocusing on the more promising direction without like any human intervention. So have you thought about this, and like how do you compare these two?
So how does the sketch guidance compare to a beam search, for example, or?
Yeah, like beam search, but in equality saturation style.
Yes, so I think the difference is that for beam search, we need a good enough heuristic to know in which direction to keep exploring. And in this case, we didn't want to rely on the heuristic and on greedily going into a certain part of the search space, but we wanted instead to rely on the intuition of the expert, because in some cases it might be feasible to have a good heuristic to make local decisions, but in other cases it might be very difficult. And in particular, many optimizations go through intermediate programs that are really bad in terms of cost compared to a heuristic.
I see. So is it fair to say that for applications, like the experts already have something in their mind that they want to have as intermediary goals?
Yes, I think the strength of the technique is when the expert has an idea of what they're trying to achieve, or at least is going to maybe explore different ideas that they have. So maybe they don't know immediately in which direction to go, but they have a couple of different ideas that they want to try out. And the benefit compared to trying out these ideas manually is that they know that the result is correct by construction, so they don't have to worry about correctness.
I see. Thanks.
Okay, thanks again, Thomas. I think you can now stop screen sharing.
Thank you.